It's my great pleasure to introduce Nikolai Zeldovich from Stanford. Nikolai's a postdoc who's been working with David Maziris both for his PhD and post-PhD at Stanford on various projects related to information flow control and security in operating systems. And before that, he's done a bunch of work on the Collective, which is a virtualization-related project. And prior to that at MIT, if I remember correctly, on event-driven code and how to bring it to multiprocessors in a way that's more meaningful and more approachable to programmers. So with that, I'll let Nikolai take over, and welcome.
Thanks very much. So in this talk, I will tell you how we can use information flow control to build secure systems out of buggy code. So why is it so hard to build secure systems today? Well, a big part of the problem is that a single bug in almost any line of code in today's systems can lead to a security compromise. And it's not surprising then that we're seeing very simple errors in web applications leading to disclosures of millions of social security and credit card numbers. And ironically, even security software itself often has bugs in it. So for example, Symantec's virus scanner, which is supposed to protect our desktop systems, had a bug in it that exposed 200 million machines to attack. So our current strategy for dealing with all of this is to find and fix every one of these vulnerabilities, from buffer overflows to SQL injection attacks and so on. But in practice, this is just turning into an arms race with the attackers of who's going to be the first one to find the next bug. And experience shows that it's nearly impossible to eliminate all of these bugs and vulnerabilities in the first place. As a result, I claim that this current strategy is simply not sustainable in the long run. So to understand this in a little bit more detail, let's look at an example application and see what does it mean for an application to be secure. So here we have an example web application, such as a job search website, and it's composed of multiple layers of software. At the highest level, the web application cares about security of different user profiles, perhaps ensuring that one user cannot look at someone else's resume. One level down, the web server controls what different web browsers can make different HTTP requests to the server. Further down, the operating system has some mechanism for protecting different Unix users from one another. And at the bottom, hardware has some mechanism for ensuring the kernel is not tampered with by application code. What all of this means is that if we want the system as a whole to be secure, code at every one of these layers has to be bug-free. Even if we somehow manage to come up with perfectly secure hardware and a perfectly secure operating system, the application itself could still be compromised because there are millions more lines of code in all these layers above the operating system that have to be bug-free in order for the system to be secure. So what can we do in this situation? I claim that as long as security of our systems continues to depend on the absence of all of these bugs, we're basically doomed. However, in this talk, I will tell you how we can potentially build secure systems out of potentially buggy application code. So to understand how this is going to work, let's step back and rethink security for a second. At a high level, most security concerns we have in a system relate to the data we have in the system, not to the code operating on the data. So I don't want a copy of my financial data being sent over the network, and I don't want a phishing website getting a copy of my password. And in a web server, one user's profile shouldn't be sent to a different user's web browser. Suppose we could actually enforce data movement in this manner. Then if we could ensure that our data was secure in a system, we wouldn't have to care so much about what the code was doing with our data. And this would achieve our goal of building a secure system out of potentially buggy code. So currently, all of these data movement policies are, of course, present in our systems, but they're being enforced by code all over the place, from the operating system all the way up to the web application. And this means that code at every one of these layers has to be trusted, as I will indicate with the yellow color on my slides. So what I will argue about in this talk is that we should abstract away this notion of protecting data in a system into a low-level common protection mechanism provided either by hardware or by an operating system at a low level, and then use this mechanism at all higher levels of software to enforce their security such that those higher levels will no longer have to be trusted. In particular, I will argue that this common mechanism should be about controlling data movement in a system, which allows us to cut across layers of abstraction in software. So if you think about it, the same bits of data we have in hardware also represent processes and files in an operating system, and also correspond to user profiles or your financial data in a tax application. What this means is that any security policy we have about high-level data objects can be directly translated into a security policy about low-level bits of data that the operating system or hardware can understand and can then enforce data movement on those bits at the low level. And this is what's fundamentally going to allow us to build a secure system out of potentially buggy code. And later on, I will show you how about 100 lines of code can enforce pretty interesting security policies for a complex application. So this high-level idea of controlling data or information flow control has been around for a while. It was originally used in military systems in the 70s to ensure that processes with access to top-secret data couldn't write that data out to unclassified files. However, while these systems did provide an information flow control mechanism at a low level, they didn't actually allow higher levels to make use of that mechanism. So that if we were to build a web application on top of a military operating system, we would have to re-implement all of our protection mechanisms from scratch, putting us exactly back where we started from in terms of the amount of trusted code we have. Now, more recently, this idea of information flow control has resurfaced in the context of building secure web applications. So systems like GIF and Flume provide an information flow control mechanism that web applications can use to enforce their security policies. However, in all of these systems, there are still millions of lines of code in these remaining yellow blocks on that slide that have to be bug-free in order for the system's security to hold. And what I will argue about in this talk is that information flow control should be enforced by the lowest possible component in the system as the fundamental protection mechanism. And all other protection in the system should be built on top of this one idea. And later on, I will show you how information flow control can be enforced in a small 20,000 line OS kernel, or even largely in the hardware itself. So conceptually, this information flow control mechanism is going to be quite simple. We're going to associate a label with every piece of data in the system. And as I mentioned earlier, this label will cut across all layers of software abstraction. And this label is going to follow the data as it gets copied or moved around in the system. And ultimately, the same label will control what can happen to the data. So for example, this label might ensure that no copy of my financial data can be sent over the network. And then if we get this one simple mechanism right, the hope is that most of the other code in the system is not going to have to worry about security. So while this seems like a fairly simple mechanism, it's not entirely clear how we can actually build all other protection in our system on top of it. So for example, how do we implement things like user accounts with information flow control? Or how do we give users and applications access to the same mechanism that is being used to constrain them in the first place? Or if we do that, what happens if a user misuses this mechanism and creates a process that they can no longer communicate with? Or how do we even manage a system where the system administrator doesn't necessarily have the rights to talk to most of the processes on his own machine? So in this talk, I will present to you 3 systems that I have built that follow this idea of providing information flow control at the lowest level and building security on top of this. So the bulk of this talk will be about this operating system called Highstar that I built together with my advisor and a fellow student, Silas, at Stanford. I will then also tell you about a system called Loki that, if we can change hardware, allows us to enforce information flow control largely in the processor itself. And finally, in cases where we have a distributed system of multiple machines, I will also tell you about a system called dstar that allows us to scale information flow control to distributed systems. So let me start out by talking about information flow control in this operating system called Highstar. And I will start out with an example application of a virus scanner. So on the left here, we have a virus scanner process that reads our private user data and perhaps writes out some temporary state. And on the right, we have an update process that downloads new versions of a virus database from the internet. So I don't necessarily expect this virus scanner or update process to be malicious by design, but as I mentioned earlier, even well-meaning Symantec software had vulnerabilities in it that allows an attacker to take it over. And just recently, there have been a number of vulnerabilities discovered that allow virus scanners to be taken over by specially crafted file contents. So to the extent possible, we should probably treat both the virus scanner and the update process as malicious, because they can be quite easily taken over by an attacker. And in this situation, the question is, can we ensure that even a malicious virus scanner and update process cannot compromise our security? Namely, we want to ensure that our private files are not corrupted or sent out over the network. So at a high level, this seems like a perfect job for information flow control. We will associate some kind of label indicated by a red color on this slide with our private data. The same label will be also associated with the virus scanner and any temporary state that it saves. But this label will somehow prevent the virus scanner from sending any of this data onto the network. So can we enforce this simple policy in an existing system like Linux today? So let's see what can go wrong here. To start with, the virus scanner can just send the data out onto the network directly. To fix this, we can somehow have to restrict access to sockets for the virus scanner application. But in that case, the virus scanner can also collude with the update process. And if both of them are malicious, the virus scanner will hand the data to the update process, which will in turn leak it onto the network. To prevent this, we have to somehow control interprocess communication mechanisms. But the virus scanner can then also write your data out to a temporary directory, and the update process will read it from there. Or the virus scanner will set its process title to the contents of your private file, and the update process will run PS. Or the virus scanner can modulate disk space usage in some detectable fashion, or it can lock different regions of the virus database. Or it can even take over some other process in the system which will leak the data out for it. It seems like this list of ways of leaking data on Linux just keeps going on and on. Is there any hope for us to actually enforce this simple information flow control policy? Well, it turns out that the problem is that the Unix API, at which I have been describing things up to this point, is simply too high level for controlling information flow. So the Unix API, shown with a blue line on this slide on the left, has two fundamental problems. One is that there's just too many ways for data to move around inside the kernel underneath this API, as I just illustrated with all these examples. And the second problem is that fundamentally Unix associates protection with processes and files in the system, not with the data in those objects. And as a result, a process can easily launder data by reading it from one file and writing it out into a different file with different protection permissions. As a result, enforcing information flow control at this Unix API level, as indicated with this red security boundary, is simply a bad idea. So to solve this problem, this operating system called Highstar separates out the traditional programming interface, such as the Unix API, from the kernel interface. So the Highstar kernel interface, which enforces security in our case, has two key differences from Unix. One is that it has very few ways for data to move around, allowing us to control information flow. And second, it fundamentally associates protection with the data in the objects, not with the processes or files themselves. And then we can actually implement traditional APIs like Unix by providing a translation library that runs the user space without any special privileges. And the challenge in all of this is, how do we come up with this kernel interface such that on one hand the kernel is small enough for us to enforce information flow control with some assurance that we've done it correctly, and at the same time the interface should be generic enough for us to be able to implement things like the Unix API and capture the security policies we care about, such as the Unix security policies and those of different applications. So the approach we're going to take is as follows. The kernel is going to provide a simple interface consisting of 6 types of kernel objects I will describe in a couple of slides. And this interface is going to be expressive enough for us to build a Unix-like environment on top of it. And the only protection mechanism provided by the kernel will be an information flow control mechanism, which will be egalitarian in the sense that any process in the system can make use of it, not just the system administrator. And then we're going to build everything else on top of this small collection of primitives. And what gives us some hope that these are the right primitives, if you will, is that, as I will be illustrating in the rest of the talk, the same set of primitives seem to be solving a whole range of different problems for us in different contexts, giving us some hope that we've hit upon some kind of common denominator here.
So you said that one of these primitives, like any piece of software, can use them. That seems to be an opportunity for opening a door to security flaws rather than closing. So when you continue your talk, could you tell us how that in fact doesn't create more opportunities rather than fewer?
So
the operating system provides some protection just through its normal protection mechanisms.
Sure. So the question is, how do I avoid kind of opening up more problems? And I hope I will illustrate that in the rest of the talk. And if it's unclear at some point, ask me again. Question?
So instead of designing a new simple interface, instead of considering Unix, you would consider a lower level interface like a microkernel interface, which has a few simple types of objects and ports for communication. Would that be better adaptable to information flow control?
So it turns out that message passing is fundamentally the wrong abstraction for information flow control, because in message passing, you have to allow bidirectional communication along any interesting dimension. You have to send a read request to the file server, and it will respond back to you. So then, as far as the kernel is concerned, all interesting parties can somehow communicate through some transitive set of links. And as a result, the kernel cannot enforce any meaningful isolation policy on its own. It can certainly do so in concert with these trusted user space file servers, Unix servers, and so on, like in Mach. But it does bloat your trusted code base to include these user-level servers, and we avoid that in Highstar. So I will now describe to you these mechanisms in a bit more detail, and then show you how these mechanisms can be used to achieve more interesting functionality in user space. And then I will argue for why these mechanisms actually provide better security than systems like Unix or Linux do today. And finally, I will show some applications that we're able to run on top of Highstar. So to start with, here are the 6 kernel object types Highstar provides. 4 of them are probably familiar to anyone who's looked at an operating system. We have segments, threads, address spaces, and devices. And what this means is that we can implement all the traditional things you expect out of an operating system in Highstar. However, we also have 2 unique primitives in Highstar that are key to achieving some of our security guarantees. We have an object called a gate, which is our interprocess communication abstraction. And we have an object called a container, which is similar to a directory in Unix, in that every object in Highstar has to reside in some container, and they form a tree like directories in Unix. And each one of these objects has a label associated with it that describes the security properties of the data inside of that object. And the way I will describe labels in my talk is by analogy of colors. So I will use the color yellow here to indicate objects that contain my private data in them, perhaps. So if all 3 of these objects, a thread and 2 segments, have this yellow no smoking symbol, that will indicate that all of them might have a copy of my private data in them, and information can flow freely between all of them. The rule is that yellow data can only flow to other yellow objects. We can also have multiple colors of data in a system. So if the object on the right is labeled purple, it contains some other user's private data, and information cannot flow to it from my thread or vice versa. And finally, we can also have multiple colors of data in a single object's label. So if the thread in the middle is labeled yellow and purple, it contains both users' private data, so it can read both of our segments, but not write either of them, because that would leak information about the other user. And this would form a perfectly secure system in the sense that all of my data keeps being labeled yellow, but at some point I want to get the data out, and for this reason, we introduced the notion of ownership of data, indicated with a star symbol. So if this thread in the middle has a yellow star, it can remove yellow taint, if you will, from objects, so it can take the data in my yellow object on the left, and perhaps after encrypting it in some way, write it out to the object on the right, which doesn't have a yellow label, and I'm explicitly trusting it to do so. And the way these labels come about in the system is through an egalitarian mechanism that allows any thread in the system to request a new category, and the new thread gets ownership of this category, and can then use this category in labels of different objects to specify information flow restrictions. So this forms the entire kernel interface I've been talking to you about, so these 6 kernel object types and the use of labels for protection. And now I will show you how we can use these mechanisms to implement interesting things above them. So to start with, we can implement traditional operating system abstractions like a process. So in Highstar, a process is a container with a thread that contains an address in an address space and some segments to store the data. And this actually results in a fairly usable Unix-like environment. So my laptop here is actually running Highstar. So I can switch to a different virtual terminal and log in as myself, list my files, check that I'm running as my user account, list the running processes, and so on. But the interesting thing is that this is not just another clone of Linux. So if you recall earlier, we had this example of a virus scanner application where we wanted to make sure that a malicious scanner process cannot leak my private data. We can easily do this in Highstar by labeling my private files yellow. The virus scanner and any temporary state it saves will also be labeled yellow, but that label will prevent the virus scanner from leaking my data to the network or to any other intermediate process. And we can enforce this without any need to audit the virus scanner's code for security, which is a great benefit here. And the only remaining question is, how do I now get the output of this virus scanner process sent to my terminal, which is not necessarily labeled yellow in this system? And this is exactly the reason why we introduced this notion of ownership in the system. So if we have this process on the right called wrap that owns the corresponding yellow category, it can take the yellow output of the virus scanner process and send it onto my terminal. And in fact, the only thing this wrap program is being trusted to do here is to do exactly that. And by doing so, it will enforce this interesting security policy on this virus scanner application. And we can also use information flow control to prevent file corruption as well. So if we label the virus scanner purple, but my files are not labeled purple, that will prevent the virus scanner from overwriting my files, although it can still read them. And it can also still send the output to my terminal because we'll give the wrap program this purple star. So we've actually implemented this in Highstar as well. So we have this wrap program that can run an arbitrary Unix application with 2 additional security guarantees, namely that the application cannot corrupt or overwrite any of your data, and it cannot disclose it onto the network. And all this wrap program needs to do is to set this label on the process it's running, consisting of 2 fresh colors, and relay the output to my terminal. And this is done in 140 lines of code. And the kernel does the rest of the heavy lifting, if you will, that enforces this isolation security policy. Question?
It seems as if, unless I'm misunderstanding this weakens the services you can provide to the other applications. In particular, can't a yellow program somehow, you yourself mentioned earlier the possibility of encoding the data somehow by using up certain amounts of disk space to get a message out. So does this mean that other processes then can't see how much free space is on the disk? And if they try to open their own files, can't they discover that by trial and error somehow?
So we have a quota mechanism, and we try to prevent those covert channels as well. I will try to get to it in the rest of the talk. Yeah. So I can quickly demonstrate this. So I can run wrap on any program you would otherwise expect to have in Unix, like ls, and it works. But I can also run wrap on a virus scanner called ClaimIV that I downloaded from SourceForge. And it seems to check my files for viruses and sends the output to my terminal, but I don't actually have to trust it to do the right thing in any sense. And in fact, if a friend of mine sends me this mystery shell script that on a traditional Unix system would disclose my private key and remove my home directory, as long as I run this under a wrap, nothing bad happens to my system. So it cannot disclose my private key or modify my home directory in any way. So now let me move on to an interesting question. Oh.
Before you move on, how are colors, who decides what piece of data gets which color? And is that, or did you say this?
So it gets assigned by application. So whenever you create a new object, the creator of the object has to specify the label for the segment, for example. And it's subject to a few restrictions based on the caller's own label. So if the caller has no stars, the label of the new object has to be equal to the label of the thread creating the object. However, if the thread has some stars, it can decide whether to add or not add that color to the label of the new object. So it has the freedom in those dimensions.
On first blush, in other words, just listening to this for the first time, that seems secure, that labeling process?
So it seems to be, and we've done some model checking and so on that seems to support it as well. And I will get to it later on. Question?
What happens when a process does something it does not have permission to do?
It gets an error from the kernel saying your labels don't match. You can do it.
I'm worried about covert channels, right?
So we do try to address covert channels, and I will get to it later. Quick question?
So there's only one process. A process with a star can't hand that star to some other process, or
yes. So we allow granting privileges, and it's not exclusive ownership. You can have many processes with the same colored star in the system as well.
So both stars and no stars.
Yes. So to understand why these mechanisms are more secure than what we find in Unix or Linux, let's consider another way that information can leak on a Unix system. So here we have the same scanner and update process that shouldn't communicate from the scanner to the update process. Suppose we actually ensure that no interprocess communication mechanism exists that bypasses this restriction. Suppose now that they also share a read-only file descriptor, perhaps corresponding to the virus database. At first, this seems secure because the file descriptor is read-only and neither of them can write to it. But it turns out that in Unix, there's a seek pointer associated with every file descriptor. And the scanner process can potentially seek the file descriptor back and forth, and the update process will observe the seek pointer to learn information that it shouldn't have. The reason this is a potential problem in Unix is that file descriptors, along with other Unix abstractions, are implemented inside of the kernel underneath the red security boundary here. This means that we have to very explicitly reason about the security properties of all these abstractions, file descriptors, file locks, process titles, and so on, in order to ensure security. On contrast, in Highstar, file descriptors and all these other abstractions are implemented inside of the Unix library above the security boundary. This means that we don't have to explicitly reason about all these different abstractions for security to hold. So for example, with file descriptors, there's no analogous problem in Highstar almost by design. So every file descriptor in Highstar is implemented with a segment object that contains all the state for the file descriptor, including the seek pointer. And if the scanner process on the left were to be tainted yellow, it would automatically not be able to write to the file descriptor because of one simple check provided by the kernel, namely whether information can flow from one object to another, or in other words, just object read and write checks. So in this manner, we've actually reduced the security of our system to one simple check that we have to get right. And in fact, this label mechanism is the only fundamental building block provided by the kernel for security. It's a very low-level mechanism in the sense that it just controls when information can flow from one object to another. But at the same time, it's also very expressive in the sense that we can use it to implement Unix user IDs, Unix groups, and so on, and also can repurpose it to implement application security policies, such as those in the wrap example I showed you earlier. And in fact, this mechanism is egalitarian, as I mentioned earlier, in that anyone can allocate a new color of or category in the system and gets the star to specify their own information flow restrictions. And in fact, there's not even any notion of a super user in the kernel to get around these labels. This is not to say, of course, that we don't have a notion of a system administrator. We want some guy to back up our files and to reset our password if we forget it. But this is all done very explicitly by convention. So if we have two users here, they might very explicitly grant their privileges indicated by these stars to the system administrator for him to be able to manage their user accounts. But this is all done inside of this Unix library above the security boundary provided by the kernel. What this means is that users can use the security interface of the kernel without granting privileges to the system administrator. So for example, if this user Bob on the right wants to run an SSH agent process that holds his private key for authenticating to other machines on the network, he can prevent the system administrator from getting access to that private key by labeling the process with this new green category. And as long as he doesn't give the corresponding green star to the system administrator, the sysadmin won't be able to get his private key. Now, there's a potential problem here that what happens if this SSH agent process goes nuts and allocates all these different colors and refuses now to talk to either the user or the system administrator or anyone else in the system and starts chewing up CPU cycles. The way we solve this in Highstar is by very explicitly controlling all resource allocation. So in Highstar, every user has a home container that stores all of the kernel objects corresponding to their processes and so on. And when the user starts a new process like SSH agent, it goes into their home container. At this point, if this SSH agent process goes nuts and gets all these colors and refuses to talk to anyone else, the user can still remove that process from their home container and have the kernel garbage collected without necessarily having the right to go and poke at that process directly. Question?
I'm wondering, of the things you've run on this or ported, either in the library or at the user level, how many things don't work because their implementation breaks the policy that you want?
So in the Unix environment, if you don't impose any extra security policy, most things just work the same as in Unix and with the same security benefits and drawbacks. Of course, it depends on what security policy you do impose then. And of course, things do break, and we are taking the point that security should take precedence over functionality in those cases.
So in the library, how much did you write all of that, have to rewrite all that from scratch, or did you?
Yeah, so the library is completely written from scratch. Question?
Authenticate to Highstar? Is that how the initial shell is created? But something has to have every right to create the initial shell for a user.
So when you first start Highstar, there's a system administrator shell that gets created that has no categories, no privileges, and nothing at all. And from there on, it starts by creating a new category for every user account, a new category for every process, and so on. And of course, there's some notion of forward secrecy here, namely that if the system administrator runs Highstar in a VM, no one will ever be able to tell from the outside necessarily, and he will be able to impose his super user will on the entire system. But as long as you do set your label accordingly at some point in time, then going forward, there is no super user that can subvert that.
So earlier you said that the design with a file system would mix all the data from various people, therefore you wouldn't be meaningfully isolated. So does this mean that I have a file system per user?
I will get to the file system in 5 slides. So the same container mechanism also allows us to manage the system without super user privileges as well. So the only special privilege the system administrator does have is that he has access to the top-level container in the system. So he creates subcontainers for different users, and if the user needs to be deleted or if he needs to give more resources to someone, he can adjust the top-level container's resource allocations. And he can remove a subcontainer if he need be. But he doesn't have any inherent right to access the data inside of those containers. So in other words, if the root's password in the system is compromised, it doesn't mean that the data of different users has to be compromised as well. So in fact, the same container mechanism is also used to implement the file system in Highstar as well. So traditionally, you need some mechanism to store data persistently on disk to implement a file system. And in Unix, this is done by providing 2 very different mechanisms for storing data in memory and on disk. So in memory, you call malloc, or you extend your breakpoint, and so on. But to store data in the file system, you would call open, read, write, close to access data on disk. As a result, there's also 2 very different ways to protect data in memory and on disk. And in Highstar, we get around this problem by reusing the same mechanisms I've already shown to you to implement the file system as well. So all that we need to do now is to provide a single level of storage in the kernel, much like in the Multics or Eros systems previously. And what this means is that all of these kernel objects are stored persistently on disk, and their in-memory version is just a cache of their disk contents. So having that in mind, we can now implement the file system using containers and segments. So directories naturally map to container objects, which have a special segment object in them that maps file names to the actual objects implementing those files. And the nice thing about implementing the file system with the same abstractions is that the same protection mechanism can also be used to protect the file system as well. So in this case, if I don't want my mail ending up on my website, I can label my mailbox file yellow, and the kernel will automatically ensure that my mailbox doesn't end up in my public HTML directory. Another nice benefit of having a single level store in an operating system is that it avoids the need for super user privileges at system boot up time. So in Unix, the system administrator needs super user privileges to start all the privileged daemons when the system boots up. However, because of the single level store, processes in Highstar don't actually notice a hardware reboot. So I will quickly demonstrate this on my laptop. So if I try to reboot, well, that's what happens when my label doesn't match. But if I log in as root now, I can reboot my laptop. And what's going on now is that the kernel is checkpointing all the kernel objects implementing this Unix environment to disk. And at that point, the machine will physically reboot along with the kernel. And when the kernel comes back up, it will read all these objects back from disk and resume execution exactly where it left off. So one nice thing is that if we had that user Bob with his SSH agent process, the SSH agent process will come back to life without any need for the system administrator to restart that process. So if I boot my kernel again, it's going to read all the kernel objects and should bring me back exactly to the shell where I left off. So now let me get to so of course, you would want to reboot sometimes in a system in the sense of killing off runaway applications. And we support that in Highstar as well, except that we very explicitly separate out the notion of rebooting user space applications from rebooting the kernel and hardware. So what this ureboot command does that achieves the equivalent of a Linux reboot is that it deletes all the process containers in a system while keeping all the file system containers intact, and then simply starts a new init process in the system. And in a few slides, I will show you how the gate mechanism, I haven't quite described yet, allows the init process to not require super user privileges either. So now let me move on to the question of how do we know that this Highstar kernel is enforcing any of these security guarantees correctly? So at a high level, what gives us hope is that information flow control very precisely defines the goal we want to achieve. Whenever information is flowing from one object to another, all we need to do to decide whether this should be allowed is to compare the labels on the relevant objects. There is no semantics that we have to consider in this security check. And of course, the long-term goal here, maybe 10 years down the line, is to verify that our implementation correctly enforces this invariant. And at least in Highstar, we know exactly what we want to verify, unlike systems like Unix, where security properties are not precisely defined. But in the meantime, the challenge is how do we ensure that our design at least is sound so that we can verify it later on? And in particular, in the context of information flow control, the question is, what do we do about all these covert channels? So in Highstar, we broadly classify covert channels into two categories. So the first is covert channels that are part of the implementation and not part of the official design or specification of the system. These kinds of covert channels are almost impossible to eliminate. There's timing channels, cache lines, and so on. But luckily, well-designed applications or well-behaved applications shouldn't depend on the presence of these covert channels because they're not part of the system's API. As a result, we can mitigate or fix these covert channels by using well-known techniques without breaking these applications. A much more troublesome kind of covert channel is one that's actually inherent in the design or specification of the system. And these kinds of covert channels we cannot fix or mitigate later down the line without breaking applications. And it is precisely these kinds of channels that we'd like to avoid in Highstar. At a high level, the way we achieve this in our kernel is by very explicitly labeling every piece of the kernel interface. So every kernel object has a label associated with it. All resources have a label associated with them, where resources are represented by containers, and so on. But there's a potentially troubling question of what do we do with the information inherent in the label of objects themselves. So, for example, if you remember earlier, we had this example of a file descriptor in Unix whose seek pointer was conveying information. You might imagine that in Highstar, a mutable label of an object can similarly convey information. So, to understand what it means to have a covert channel in the specification of a system, consider this simple example. On the left, we have a malicious process that has a secret bit of data that we would like to prevent it from leaking onto the network. And the way we do this is by labeling it yellow, which precludes it from talking to the network directly. Now, in many system designs, this process can actually leak this bit of data onto the network with the help of two colluding processes running on the same machine. So all it needs to do is to send a message to one of these two processes, depending on the bit it wants to leak. And in many systems, the act of sending a message to another process propagates the taint or the label to the recipient. At this point, this colluding process on the bottom is also labeled yellow to prevent it from leaking information onto the network. But of course, any network attacker can observe that process 0 can now talk to the network, but process 1 no longer responds, and can therefore infer that the secret bit of data was 1. So a number of systems have tried to solve this problem in the past. So programming languages like GIF relied on compile time checks to avoid runtime covert channels through label comparisons. But unfortunately, this restricts the kinds of dynamic behaviors you can implement in the system. So for example, a statically checked programming language application cannot do dynamic behaviors like the wrap example I showed you earlier. A number of operating systems like IX or Asbestos also gave up on trying to close this covert channel and said, well, maybe this is an inevitable property of any dynamically labeled system. Turns out that they couldn't quite find the right kernel abstraction to provide it to avoid this kind of covert channel. And of course, military systems that really care about covert channels relied on fixed labels to avoid them. But the only reason they can really do so is because they have very few labels in the system. They have secret, top secret, and so on. And as a result, they cannot do dynamic applications like wrap either. So the way Highstar solves this problem is to make most object labels in the system immutable. So in particular, every non-thread object in Highstar has a fixed label that prevents an attacker from modulating it to leak information. But because this is not quite dynamic enough for us, we allow a thread to change its own label in the system. And the reason this is safe is that any information that a thread already had that went into the decision to change its own label is already available to the thread, of course, and it can leak that information directly without resorting to the label mechanism. And of course, we only allow the kernel only allows threads to change their label by adding colors, not removing them to enforce security. So to see how this simple idea allows us to still have all the behavior and functionality we would want in a system, let's take a look at this example of a job search website. So on the right here, we have a database server that has a database of job listings. And on the left, we have a job search process that would like to query this database to look for available jobs. And what we would like to have is that the fact that this guy is looking for a job is not exposed to anyone, not even the database here, to make sure that his employer doesn't find out that he's looking for a job and fire him perhaps. But how can these two processes communicate with one another when their labels are incompatible? So this job search process cannot change the label of the database server thread and vice versa. And otherwise, how do we bootstrap this communication? The way this works in Highstar is through this gate abstraction that I mentioned earlier. So the database server creates a gate object that explicitly binds the database server's privileges, indicated with this purple star, with code in the database server's address space. At this point, if the client thread invokes this gate on a query it wants to run on the database, the gate actually switches the client's own thread into the server's address space and gives it the server's privileges. At this point, the client's thread starts executing in the server's address space, running his code, and he has the purple star. And the thread can use this purple star to read the job listings database, although it cannot write back to the database because the yellow no smoking symbol prohibits it from doing so. And now it can process the query and send the results back to the client's own address space using all the same thread. So in this manner, we can actually use a system with largely immutable labels to still implement interprocess communication and all the other functionality we would want in a Unix-like system. So this gate abstraction also allows us to avoid superuser privileges when restarting processes in the system. So if you remember earlier, we had this reboot command that would kill all the processes and start a new init process. And the reason to do that is processes are typically stuck in an infinite loop of some kind or are those sorts of problems. But these gates are very passive objects. They don't execute code like a thread. And there is no reason to necessarily kill a gate across a ureboot. And as a result, the ureboot command leaves the gates intact, avoiding any need to recreate the gate when the system starts back up. So to summarize the design of the Highstar kernel is that a small number of mechanisms provided by the kernel seem to be solving a large number of problems for us. So the container object allows us to allocate resources in the system and implement the file system. And while I didn't mention it earlier, it also allows us to discover the labels of other objects in the system. This gate mechanism allows us to implement inter-process communication with largely immutable labels, and also helps us avoid superuser privileges for restarting applications. And finally, the label mechanism itself allows us to implement Unix user protection for this wrap example I showed you earlier, security in this database example, and as I will show you later, security in a web server application as well. And all of these mechanisms are implemented with a 20,000 line kernel, and all other functionality is built on top of this fairly simple interface. So now let me move on to some applications we've been able to implement on top of Highstar. So I already showed you this wrap example where you can run arbitrary Unix applications with a new security policy. And now I will show you how we can build a web server in Highstar out of largely untrusted code. And finally, I will show you how Unix login works on Highstar while using user-supplied password checking code as well. So to start with, let's take a look at the structure of a web server on a traditional system like Apache running on Linux. There's probably some component that accepts connections from the web browser called the listener, which then hands the connection off to OpenSSL, which decrypts the user's request. It then passes on the user's request to an HTTP component that parses the request. And perhaps that component will start some application code that will generate a PDF file based on the user's data and send the resulting PDF document back to the user's web browser. So this web server consists of over 1 million lines of trusted code that has to be bug-free in order for the system to be secure. We can greatly reduce this number in Highstar by using these information flow control mechanisms. So to start with, we can label each user's data with a different color, And then as long as we run a separate instance of the application code to process that user's data, the guarantee that the kernel provides is that that data can only escape through a component that holds the corresponding star, which in this case would be this HTTP component. So in this way, this HTTP component can now enforce security without having to trust the application code to do the right thing. So it might send garbage to the user's web browser, but it cannot send garbage or anything else to a different user's machine. Now, there's a potential problem here, namely that this HTTP component now has the privilege of every single user in the system, and if it's compromised, we're in a lot of trouble. Turns out that we can also use information flow control mechanisms to prevent that from happening. So if we have a series of user authentication agents in the system, one for every user, we can have the HTTP component very explicitly authenticate the user by sending that user's password to his authentication agent. And if the password is correct, the agent will give the user's star back to the HTTP process. So at this point, we no longer have any fully privileged code running in application in this case. And in fact, we can use information flow control to also prevent the OpenSSL library from being part of the trusted computing base here. So if we run a separate instance of the OpenSSL library for every TCP connection labeled with a different color and give the corresponding stars to the listener and HTTP processes, the guarantee that the kernel will provide is that the OpenSSL library, even if it's malicious, can only communicate with the listener process, which will forward the data to the right user's web browser, or with the HTTP process, which will act on the plain text. So the worst case is if the OpenSSL library is malicious, it can potentially send plain text or garbage data to your own web browser, or send a garbage request to your HTTP component, but it cannot disclose your data to anyone else on the network. And it turns out that we can also prevent the OpenSSL library from being able to disclose the RSA private key of the SSL certificate as well. So all we need to do there is to insert a small 4,000-line RSA daemon in front of the RSA private key in the system, which will expose a signature generation interface to the OpenSSL library without giving it access to the RSA key itself. So the OpenSSL library can sign certificates to establish a session key without having access to the raw bits of the certificate key, such that even if the OpenSSL library is compromised, we don't have to revoke our web server certificate. So the high-level bit in all of this is that the security of this web server is being enforced by a small fraction of the overall code. Namely, the security of the server here depends on these yellow trusted components, which total about 6,000 lines of code in the system, out of about 1 million lines of total code. And in fact, we don't even necessarily have to write all these 6,000 lines for the web server itself. Because these labels are such an egalitarian mechanism, we can actually reuse the same user authentication agents for authenticating users in the web server and in Unix as well. Because these authentication agents simply hold different colored stars, they don't care what the stars necessarily correspond to in the application. So we use the same agent code to manage stars in the web server and in Unix and in other cases where we need authentication. And the label mechanism also allows us to implement quite interesting functionality in these agents. So to start with, because each user has their own agent, we can also allow the user to control their own agent to support different kinds of authentication mechanisms. So if I want to support one-time passwords or challenge response schemes, I just need to modify my own agent without having to agree with the system administrator. But this introduces a potential problem, namely what happens if, when logging in, I mistype my username and hand my password to the wrong agent. It turns out that the same information flow control mechanism also allows us to prevent this from causing any harm. We can use information flow control to ensure that even a malicious authentication agent can only give you the privileges back, or not, but it cannot do anything else with your password. So to summarize what I've told you about Highstar is that by providing information flow control in an operating system kernel, we can actually have the kernel then enforce application security policies. So all that this takes is a small part of the application has to specify security policies using labels. And I showed you how about 6,000 lines of code can do this in a web server, or about 140 lines of code for this wrap example. And then a 20,000 line kernel will enforce the security policy for this wide range of different applications. And the hope is then that the rest of the application can be buggy without negatively impacting the security of the overall system. So now let me very quickly move on to two other systems that I have built. So one is called Loki, which enforces information flow control largely in the processor itself. And the high-level picture there is very much the same as what we did with the Unix kernel in Highstar. So in this case, we take the fully trusted Highstar kernel on the left here, and we break it up into two components on the right. One is a kernel library now, if you will, which is not fully trusted. And below that is a software security monitor component that's much smaller than the total kernel. And that security monitor translates the kernel's security policies in terms of labels into hardware security policies in terms of tags on words of physical memory. So we've actually implemented this, and we took a regular Spark processor, implemented in VHDL, and we modified it to tag physical words of memory and synthesized it onto an FPGA. And the high-level bit is that we're able to reduce the amount of trusted code by more than a factor of 2. And the hardware parameters look quite reasonable as well, so it still runs at the same clock speed. It incurs about a 10 to 15% increase in hardware complexity, and it incurs about a 1% slowdown in terms of running time. And while it still runs the same Highstar operating system, same Unix library, same web server, and so on, the security of most of these things is being enforced largely in the processor itself. And now we'll briefly mention this system called DStar that allows us to extend information flow control to distributed systems of multiple machines. And the high-level idea there is that we can encode labels of network messages into the messages themselves and have individual machines enforce the corresponding security policies locally using the Highstar operating system or even Loki. And all this requires is about 5,000 more lines of trusted code to translate labels between the local operating system representation and one in network messages and vice versa. And this shows the generality of information flow control, that it allows us to very naturally scale to multiple machines without giving up any of the security guarantees we got. So for example, we can take this Highstar web server I showed you earlier and scale it to multiple machines while retaining the same security properties as on a single Highstar system. So to summarize what I've been telling you is that by providing information flow control at a low level in all these kinds of different systems, we can build more secure systems on top of these abstractions from Buggy code. And more generally, I'm interested in finding interesting security mechanisms that allow us to build systems that will be secure by design, if you will. So perhaps one direction is to find better hardware mechanisms that can enforce information flow control in existing systems like Linux or Windows today. Or maybe better network security mechanisms that will allow applications to control the security of their own packets on the network. Or maybe mapping this idea of protecting data in an operating system to cryptography, so that even if the kernel is compromised, the user's data is still secure. Or maybe we can use information flow control to provide more principled security mechanisms in a web browser, so that we can more easily create mashup applications or prevent cross-site scripting attacks and so on. And I think this idea of information flow control also lends itself to implementing things like transactional mechanisms provided by an operating system, which I think would be quite useful in the different classes of applications as well. And of course, the long-term goal in all of this is to prove the security of these systems. And to this end, we've done some model checking, some static analysis, some symbolic execution, and so on, to look for problems in our implementation. Although, of course, that's quite an ambitious goal, and we're not anywhere near being done with that.
Well, I thought that was really gutsy of you to reboot your machine in the middle of the talk. You must have had an interesting bug or two developing this, though, erasing your disk or resetting something. Can you talk a little bit about the development process?
Yeah, so there's an interesting class of bugs, namely that this execution is persistent for all time going forward. So one time I was developing this and I had a shell open on the console and I accidentally exited out of that shell. And it turns out that no amount of rebooting will ever bring a shell back, so my execution was basically over, including my entire file system and so on. So I had to go in manually and create an empty shell for myself and so on. So there was an interesting class of bugs that comes up because there is no way to reset, create a thread out of nowhere anymore in the system.
As you presented it so far, it seems like whoever has the star is trusted with both the confidentiality and the integrity of the data, because it can either publish it or modify it. Is there any way in Highstar that you can separate those two notions, or is it just encoded in idioms of labels?
It turns out in Highstar they are actually quite separate, and I just present them as joint in this talk.
If you could go back and start over again, what's the first thing you'd change?
I think the representation of labels that I didn't actually present in this talk that Highstar does have is unnecessarily complex. So in some of our later work, like this D-star distributed system, we greatly simplified our label implementation and conceptually what a label means. And I think that's one important change. The other is simply anecdotally coding the user space environment better. So that when we came up to this, we said, okay, the kernel is going to be really secure, but the user space doesn't matter. So I spent a lot of time making the kernel right, and I just did a shoddy job of implementing the user space library. Turns out it was secure, but I needed it to work. So I still had to implement it correctly.
Seems, suppose I'm running an application accessible through the web, and that application has created this notion of user and user private data. But it also wants to write a log that belongs to the applications. Is it somehow easier to achieve both functions but protect user private data, keep from leaking data, than it would be in Linux, say? How do I achieve both these things without too much overhead decomposing the system in a way that might seem unnatural?
So one answer is that particularly in this web server that we already have, this HTTP component already can write the log out for you. So it has ownership of all these different categories, but it's not restricted in any way. So they can all append to a common log. But more generally, you basically have to express your trust by creating various gates or granting stars to the appropriate components to authorize your information, namely your request to the web server, to be written into a common log. And the only hope we have is to make that component much smaller than it would otherwise have to be.
Might end up with more secure systems than current Linux systems is the ease with which you can create these labels as opposed to the ease with which you can create user IDs, say?
So that's certainly absolutely one of the benefits, is that here anyone can create one of these labels. Even the least privileged code in the system can do so and subdivide its privileges further, as opposed to in Linux, there's only one layer of such support.